Okay. We are finally entering the part that you may be most looking forward to. It is equivalent to making a simple summary of the current stage. I will talk about this experiment next. Let's do a review of the previous course content. Then configure the experiment by the way. I'll turn on the device first. Let's analyze the topic first. In this topic are some configurations we learned throughout the NA phase. Basically all have been checked. Although there are not many equipment. But there are a lot of things to check. Let's take a look. First of all, there are 5 routers in the whole picture. 2 PCs. A switch. We're going to configure it. PC 1 writes 192.168.1.x here. Then it will not manually configure the address. Let it fetch automatically. We configure PC 2 manually. A 2.0 network segment is configured. They are not in the same network segment. Secondly, we configure subinterfaces here on the gateway. We do one-arm routing. Everyone should be able to see. Now the 2 devices cross the network segment. Since this is the case, it is to let everyone do one-arm routing. Connected to the router. We up subinterface here. This is the configuration we talked about before. We want to be on the gateway device. Also enable DHCP. Since this we have manually configured. It does not need to issue IP. Let it issue a fixed IP address to PC1 forever. Is 192.168.1.11. Issue a fixed IP for a fixed MAC. This is what we said before. Then on this device, do network address port translation PAT. Use this outgoing interface to do. Devices inside the future want to go online. This is the NAT we just talked about. We use this way of network address port translation. Point the traffic out. Further down, we want to run OSPF on the R1, R2, R3, R4 device. R1 and R2 each enable a loopback port. 1.1, 2.2, 32-bit mask. Notice 1.1 as a circle. This address can telnet this 2.2, but can't ping 2.2. We just demonstrated the ACL. In fact, it is just a ban on ping. But how can we achieve telnet but not ping? Let's wait for the demo. Look down. In the future, this 1.1 will go to this 2.2. Traffic to be sent. I hope that when the traffic passes, it goes down. When the traffic comes back, it goes up. Actually, these two are equivalent. We need to modify its path. That is, need to modify its orientation. I want the traffic to always come like this. The last one. We can only use one static route. In fact, when we do targeted ACL, for a variety of scenarios, sometimes people mess with static. So we have to stipulate. If only one static. We should write this statically here. Write a default route to the public network. So other places. We won't do too many operations anymore. Then we will start the formal configuration. We start the configuration from the switch. We must first enter the configuration mode. Let's rename the switch. Then assign VLAN to it. VLAN 10. Then VLAN 20. After the VLAN is divided, we're going to configure them accordingly. Let's do a simple plan. This is VLAN 10 on the left. On the right is VLAN 20. So we enter the corresponding interface. Interface E01. Switch port mode access. Switch port access VLAN 10. Then we enter the E02 interface of the switch. That is 02 interface belonging to PC2. Switch port mode access. Then assign VLAN to it. Switch port access VLAN 20. Okay. It's not working now. Certainly. The PC has not configured the address yet. We first configure the switch. Go to the interface where the switch is connected to the gateway. This is the 00 interface. Interface 00. After coming in. Before we enter switch port mode trunk. Have to enter another command first. I mentioned it in class before. It may not be possible to directly enter the trunk, because we have to modify its encapsulation mode first. Change it to .1Q. Then, switch port mode trunk. It entered smoothly. Next, we are going to release the corresponding traffic. Switch port trunk allowed VLAN. We're going to pass 10 and 20. After releasing the traffic, we can look at the configuration. Do show run interface. Let's take a look at the configuration under the 00 interface. We first changed its encapsulation mode here. Because the default is ISL. Cisco proprietary. We're going to make it public. But I also told everyone. For many devices in the real network now. Many Cisco devices are now .1Q by default. For some devices, you don't need to enter. But some old devices have to enter this command. Then go to modify the trunk mode. Allow VLAN 10 and 20. Change the mode to trunk. Okay. I'm done with the configuration of the switch. Let's go to the gateway to configure it next. Other equipment comes first. To save time in class, I have finished configuring the interconnection interfaces of R1, R2, R3, and R4. I won't configure the address in class for a while. You can configure it yourself after class. Let's change the name. It is Gateway. So now I'm going to configure one-arm routing. Gateway configuration one-arm routing. The first step should be no shutdown. First you have to open this interface. Otherwise, there is no way to configure it with a single arm. After the interface is opened, let's go to the subinterface. Interface Ethernet 00. We enter VLAN 10s. This .10 is not its processing capacity for VLAN 10 is identified here. It doesn't matter how many are here. But usually this subinterface is for which VLAN service. We enter the corresponding number. The subinterface is now serving VLAN 10. We will enter 10. We now modify its schema. Give it the ability to handle VLAN 10. If there is data coming in from the future subinterface, it will tear down this VLAN 10. If there is data, it will be tagged with VLAN 10. This is what we said before. Then configure the address for it. Its address is the gateway of PC1. PC1 is 1.0. Then we configure its address. 192.168.1.1. 3255 and 10. This is what we call a subinterface. Then go to another interface. Interface Ethernet 00.20. For VLAN 20 service. Still change it to .1Q first. .1Q20. This command makes it capable of processing VLAN 20. The IP address is 192.168.2.1. 3255 and 10. No shutdown. Open the interface. We have now configured the internal interface. Use two subinterface addresses. And the physical interface is opened. It just works. We are now going to engage in the external network interface. E01 interface. Interface E01. Then configure the address. IP address 10.0.1.1. Followed by a mask of 30 bits. 255.255.255.252. No shutdown. Open this interface. Then we need to configure the interfaces of R1, R2, R3, R4. I configured it in advance. But I don't know if it is configured correctly. Let's take a look together. On R1 this. Show IP interface brief. Let's check. Avoid configuration failure for a while. I just take a look at each one. Move on to the next device. Show IP interface brief. This is right. Then R3. I will not demonstrate the interface address to you in class. This is what I have already configured in advance. There's nothing to say about this. Just configure one by one. Last R4. It's okay. Now the internet address is configured. I have also used the loopback port addresses on R1 and R2. So what are we going to do now? Look. PC1 has not done automatic address acquisition. We did not manually configure the address of PC2. We just let the VLANs PC1 and PC2 belong to be divided on the switch. Then the switch is configured with the gateway. Configured the section about one-arm routing. Interconnected interfaces are configured with. Then the internet routing of the external network is configured. Then let's start configuring one by one. Let's let this PC1 get a fixed IP address forever. 192.168.1.11. Show IP. We can see the MAC. Then we need to copy this MAC here. Then to the gateway. Because we want to configure the gateway as a DHCP server. IP DHCP pool. We define an address pool. Suppose this address is called P1. We are now going to assign an address to a single host. Then I just enter host here. Because I only configure for one host now. Configuration address. 192.168.1.11. (24-bit mask). After adding a fixed IP and mask. Set up the corresponding gateway. Gateway is 192.168.1.1. Because they have to be 1.0 network segment. So it belongs to VLAN 10. After that set DNS. DNS server. 114.114.114.114. Okay. We are now done setting up DNS. After setting. We are about to bind the address. Client identifier. I'm going to tether the MAC now. I just finished copying the MAC. Paste it right now. We can't just press enter. To add 01 at the front. 01 stands for Ethernet. After that, it must be separated by 4 digits in the form of a decimal point. Then press enter. Now for a MAC address like this. I configured it with a fixed IP address. Gateway gave it. DNS gives it. It itself is a DNS server. It now only needs to open the DNS service request on the PC. So we come to PC1 here. IP DHCP. Then press enter. Start sending out messages. Now if you get the address. It is the address of 192.168.1.11. Gateway is 192.168.1.1. Then PC1 is configured. We now manually configure the address for PC2. 192.168.2.2. 24-bit mask. Gateway is 192.168.2.1. It is now configured. I now ask you a question. If now PC1 ping PC2, can you get through? 192.168.1.11 ping 192.168.2.2. It worked. Let's review the whole process. How is the single arm achieved? PC1 is the address of 1.11. PC2 is the address of 2.2. Cross-network segment access to find a gateway. The gateway is the subinterface of E00.10. 192.168.1.1. Come in interface. Then in the process of coming in, I will put VLAN tag 10 on this interface. When this interface is released, enter the subinterface 00.10 with tag 10. Because it strips the VLAN tag on the incoming interface of VLAN 10. So it will carry an empty label into the router. The router looks at you to go to 2.2. We'll see if there is a local route to go here. There is a direct connection. Come out from its 0.20 interface. Then when the data empty label wants to leave the 0.20 subinterface, it will mark this data with VLAN tag 20. Keep going down. Reserve the mark through this trunk. Then when passing through the access interface, strip off VLAN 20. Then a blank data frame is sent to PC2. The two of them will pass. This is one-arm routing. VLAN Layer 3 communication. This is the VLAN we talked about earlier. We're going to do PAT now. In fact, we just finished talking about this. We first match the traffic of the PC. Because 1 is in the 1.0 network segment. 1 is the 2.0 network segment. So we simply match all. Anyway, it is also the host of the intranet. I want them online now. Permit any IP NAT inside source. This is the fixed configuration format. Must remember. List 10. Associated with this anti-control list. Interface Ethernet 01. Then overload. Port multiplexing. The two ports have not been configured. First enter the E01 interface. It is IP NAT outside. I'm stuck in this link for a while. I think it might be a mirroring problem. Wait a while. In the process of waiting, let's analyze the configuration we will do next. We will then declare OSPF on the 4 devices. After the declaration is over, we can communicate with each other. How can we test that PC1 can access the internet? PC1 can access R1. It can go online. So wait a minute, we're going to do this 1.1. Telnet back and forth. Including PC access 2.2 where to go. In fact, I tell you this. For PC, traffic may not be able to see where it goes. But we can. Let R1 use this 1.1 as a simulated flow. Actually, that is, R1 is connected to a 1.0 network segment. You can simulate it as a PC. Anyway, the future flow will go like this. So we have many ways to verify. Okay. Enter the 00 interface. It is IP NAT inside. We are now configured. Now if configured like this, do you think it will work? Whether it can pass or not. We have a configuration that did not do. I have a default route that is not configured. I want my PC to go online now. Assuming let it go on this R1. For example, I let it ping the R1 interface. In short, this is an external address. Ping 10.0.1.2. Now, first of all, there must be a route pointing out. IP route 0.0.0.0. 0.0.0.0. A default route points to 10.0.1.2. Then let's analyze. I have done what configuration? NAT already done. The internal and external interfaces match. Then turn it into an outgoing interface. Turn with the port. This also configures. The access list matches the PC traffic. Released any refers to the default route. Then it stands to reason. If the PC wants to ping this interface now, just visit the R3 interface of the public network. Can it be pinged? You can think about it. I will ping now. Ping 10.0.1.2. No pass. Why didn't it work? Is there a problem with our configuration? Okay. We need to enter the subinterface. If you configure the subinterface here in the future, then actually, when you are going to configure the internal network interface, you have to enter the subinterface instead of the physical interface. When we typed inside just now, it is input under the 00 interface. But you don't need to cancel this order. You can go directly to the internal network interface. Interface E0 0.10. IP NAT inside. Go to 00.20. IP NAT inside. This is the configuration. After configuration, we also go back to PC1. Let's ping again. It works. The reason why I will tell you about the combination of one-arm routing. Just to draw your attention to this. Which interface address configuration takes effect? Actually, you need to configure it accordingly. Let's try it here on PC2. Ping 10.0.1.2. Okay. Also works. That is equivalent to the first two steps and we are done. PC1 automatically obtains the address. PC2 manually configures the address. Get fixed address. Configure subinterface. And then do address translation. Realize that the address of the Internet private network can communicate with the outside world. That's all we've done. We can also verify. Show IP NAT translation. We just sent a lot of pings. Then here you will find 2.2 there are 5 ICMP packets sent out. Local 5 mapping entries. Each time is a random high port locally. A port mapped to the outside world at 10.0.1.1. This is for PC2. The above 5 data packets belong to PC1. A total of 10 packets. Because each is pinged 5 times. Each is 5 ports. So our daily communication consumes a lot of ports. Everyone should know this. Let's go on to configure. Next is OSPF. Now the static line of the whole network has been configured. Configured on the gateway. Pointed to a static route out. Therefore, we cannot configure static access to the external network. It is impossible to write a static point to the private network. This can only be used on the default route. Now PC1 and PC2 can ping the addresses on the public network. That's like being able to go online. Let's start to do OSPF. Enter OSPF configuration mode. Router OSPF. Let's say this is 100. Then press enter. We configure the complete. Router ID 1.1.1.1 will be configured like this. In dotted decimal. Then declare. Network 14.1.1.0. 0.0.0.255. Declare into area 0. R1 also declares network segment 13. Network 13.1.1.0. 0.0.0.255. Area 0. The last one announces the loopback address. Network 1.1.1.1. R2 is the same. Router OSPF 100. Router ID 2.2.2.2. Then we start the declaration here. Network 24.1.1.0. This is the anti-mask. This is not a wildcard. Network 23.1.1.0. Last one. Network 2.2.2.2. We then configure. Router ID 3.3.3.3. Then we declare. This announcement is less. Network 13.1.1.0. Network 23.1.1.0. This is the last device. Router OSPF 100. Router ID 4.4.4.4. Network 14.1.1.0. Network 24.1.1.0. Okay. We are done with this configuration. Let's give it a little time to learn now. I think I should have learned almost. Let's look at the routing table. Show IP route. Let's take a look. Now R1, R2, R3, R4 enables OSPF and is done. 1.1 can tell NAT 2.2 but not ping 2.2. The loopback port on R1 can tell NAT the loopback port on R2. But can't ping. Let's do this last configuration. Let's do this routing first. PC access 2.2 goes down when it goes. Walk up when you come back. This is not easy to verify. We only need to modify the corresponding path. We can look at its routing table on R1. In short, no matter whose traffic goes to R1, R1 must look up the table and forward. Just go to visit 2.2 now. Data here. In fact, it looks at its watch. So it looks at the current table. When going to 2.2, do you go down or up? When including future reply packets, does it go up or down? We are now on R1 to see. It goes 2.2 both up and down. It's loaded. Now there are two lines. Then we will continue to check on R2. Show IP route. For R2, going to 1.1 also loads. If it goes to 2.2 in the future, it is not sure that it can go down. It's loaded. So for now, it can't be sure to go down. Then you can't go back. Because it can be seen from this that R1 is also 2. So we're going to modify. Influence their routing. Modify cost. We talked about how OSPF affects routing. Let's review again. I want R1 to go down to 2.2 now. So let's take a look at how its cost is calculated. This 110 is its administrative distance. We won't talk about this. How did this 21 come out? The default cost of a loopback port address on R2 is 1. Like walking here. Inbound direction of route convergence. This interface is 10. This interface is 10. In Cisco, by default this is a 10M interface. Then its cost is 10. So it is 21 calculated from 1 plus 10 plus 10. If we want to influence routing now, we sure want it to go down when it goes. That is. Next hop is 13. I have to increase the cost on the road of 14.1.1.4. Make it greater than 21. I told you when I was calculating. We need to change the loopback port. We will not change the loopback port today. Let's change the physical port. Because it was shown before. Let's demonstrate a different. Usually, we change the loopback port on the project to be more. But the future is not certain. If OSPF has many paths at the same time, all want to access this loopback port. If you modify it, it will also affect many roads. To be honest. In fact, it doesn't matter which one you change. Let's change the physical port first. I wish I went down now. Increase the cost above. So which interface can I change? Let's just pick an interface. Since I said it, this is a loopback port. Then this interface and this interface. Let's change the device in the middle. For example, I changed the interface of R4 to a larger size. Because routing is converged like this. So it goes under this interface. I make it bigger. It is now 10. I changed it to 100. I just make it bigger. So we go into the R4 device. Interface E01. IP OSPF cost 100. Then we look at this route. If R1 goes to 2.2 now, it seems that there is only one jump. The next hop just now seems to have 2 hops. Now there is only one left in this list. Then it means that when the data passes, it goes down. Because it checks the routing table forwarding. This is the one in the routing table. It matches this one. Then come back and hope it goes on. Which is also equal. For the top. The packet was destined for R1 when it passed. Routing is converged like this. I hope to make the above road bigger. When replying to the packet. Hope to go on. That is. When the packet comes back. Make the road below bigger. Then for R1. Routing is converged like this. For R2. This is how routing converges. If you want to make the cost of the path R2 larger, I should change these interfaces. The loopback port. This interface. And this interface. Since the above we changed here. Next. We will change the left interface of R3. Let's make it bigger. They are in opposite directions. We call the outgoing direction of the packet. So the direction is different. Change on R3. Interface E00. IP OSPF cost 100. Then we go to R2 to see the route to R1. Show IP route. Let me see if I changed it successfully. Haha, scared me. I thought this modification was invalid. For now. 1.1 is 2. Refresh it again. 1.1 becomes 1 article. I thought I changed the wrong interface. Okay. Not corrected. It takes time for it to work now. Just 2. Now going to 1.1 is only 24.1.1.4. Now R2 replies with the packet. The next hop is R4. It walks up. So, when data is being sent, you will find. This is how the traffic goes. The return traffic goes like this. Fulfilled this requirement. Now the last one left. We now want to telnet it. Let's configure telnet first. That is, I can telnet this 2.2 on this 1.1. Then we first enable the telnet function on R2. Set user. VTY04. Up to 5 users can log in. Then we still set a password. Password Cisco. One way we'll set it up later. Transport input telnet. OK. Set up. Telnet function is enabled. After opening. Let's test whether we can telnet on R1. Telnet 2.2.2.2. Password Cisco. We climbed up. It is possible to telnet. We exit. Now the last one left. Can telnet but not ping. It's actually a ping. You might say. We don't know exactly how to filter. Beginners often fall into a dilemma. When an ACL is configured. When you can't get rid of some traffic. Just configure one more. At last. A lot of rules may be entered in an ACL. Finally killed it. But I don't know which one works. Many students do this when they are beginners. It is recommended that if you are trying it out for the first time, get rid of the previous one. Then enter the new. See which one works. It is recommended that you enter an ACL in R3. Then go to Filter. Filter ICMP traffic from this 1.1 to 2.2. We actually talked about this just now. In fact, it's okay for you to do it in R2. But we're usually as close to this message as possible. Don't be the last to do it. Do it before. But I tell you, you can't do it here in R1. Because a device cannot filter out the traffic generated by itself. So you guys don't do it on this device. You can choose the left interface of R2. Or the left interface of R3. Because the traffic that comes from it is bound to go down. Your configuration above is useless. This device data will be initiated by R1 later. Let's take a look at this configuration. Access list. Excuse me. I forgot to log out. Let's get out. I now enter an advanced ACL. Because we now want to match it exactly. Access list 100. Deny current ICMP traffic. From a host 1.1.1.1. Reach another host 2.2.2.2. Echo message. There is one command missing here. Access list 100 permit IP any. Don't forget this. Although today we will not demonstrate who came to visit. But this command you have to remember to enter. After configuration. The interface has not been called yet. Call the left interface of R3. Interface E00. Enter this interface. Then we call IP access group 100 in. Then press enter. Now we are done. So now we can do a demo. First check if you can ping here. Secondly, see if you can telnet. Let's look at ping first. Because we have now isolated the ICMP message. Actually, now it should be unable to ping. That is, I am now on R1 to ping R2. If so, can ping link A? It definitely works now. Because when the data goes out now, if you do not specify the source, it is the outgoing interface. So it's definitely 02 now. 13.1.1.0. Send message to R2. R2 replies with packets back to this interface. It has this route. There is no strategy for this route. Then it can reply packets. So it can be pinged. But if you add the source, it will not work. Ping 2.2 source 1.1.1.1. This doesn't work. The percentage of successful messages is 0 out of 5. None sent. I can't ping it now with 1.1 as the source. So, we test the equivalent of can't ping it, but now want to telnet it. If you telnet it directly from here, there will be problems. Telnet 2.2.2.2. You can come in too. But it's not really coming in. This is not our experimental result. In Cisco. How to specify this? How to specify from 1.1 telnet 2.2. It has some other input methods. There is an order. IP telnet source interface loopback 0. Then press enter. This sentence means, if you use the telnet function, the default source interface is this loopback port. If you do not specify the loopback port on Cisco, by default, it is still telnet with the outbound interface of the message. So if you don't set this command, go to telnet it. Its default traffic goes like this. It must be able to come. But now we want to set 1.1 to be able to telnet 2.2. But 1.1 ping fails. We have to be stricter. Although it certainly works. But I still want to emphasize. Telnet 2.2.2.2 can still come in. This is what really comes in. Telnet is a TCP-based message. It is a service on top of TCP. It is equivalent to an application layer function. ICMP is just encapsulated on top of the IP layer. It is just a 3-layer protocol. We have made a strategy for the protocol accordingly. Then you can let the data flow through this interface. It is intercepted by the ACL attached to the interface. Then this wave of message requests will not come through. The ICMP reply cannot be returned. Then the ping fails. But this is a telnet message. All other IPs are any. Other than ICMP fixed 1.1 and 2.2. Communication with some addresses such as source IP and destination IP. We released all the remaining traffic. Then once the flow is released, the result now achieved is all messages are available. Of course, telnet packets can pass through. This is our experiment. If there is something you didn't understand, you can contact my teaching assistant to get the screen recording. You can practice by yourself after class. This is our last CCNA class. Don't think this experiment is easy. Basically, all the content involved in NA is integrated. Although less equipment. But there are many functions. This is the end of our NA phase. Okay. We'll stop here. Then we also hope that students can follow us. We are ThinkMO Education. I'm Grolin Annesley from ThinkMO. I hope today's content is helpful to you. See you next class. Bye classmates.